All right, let's get started. Oh, I'm just starting with my advertisement. In case anyone's interested. These make such great gifts for Christmas, Hanukkah, Chinese New Year. So you better buy lots of copies for all your friends, or else you can download for free from university site licenses. But that's not my subject. My subject today is how are liquid crystals like geometric packing problems? Okay, so let me begin with my quick intro to liquid crystals, right? So these are systems made out of long organic molecules with a structure like this. And on a coarse-grained basis, we could just say they are oriented in some direction, these molecules. And then we have many of them, like 10 to the 23rd. And they have a distribution of orientations. Okay? And in the typical liquid crystal phase, they are not pointing in one single direction like a ferromagnet, but rather back and forth along some axis. Okay? And so you get a distribution like this, which could be characterized by some double-headed arrow in space. Okay? And this typical phase is called a nematic liquid crystal phase. And the double-headed arrow is called the nematic director, represented by a unit vector, with the understanding that n and negative n represent the same physical state. Okay? And now, if we want to be even more coarse-grained, we can zoom out and ask, how does this average orientation vary over long length scales? It might not be uniform. It might be varying as a function of position, like this, so that there's thousands of molecules pointing mostly this way over here, mostly this way over here, okay? And then if you have a variation like that, it costs elastic free energy. That's what this talk is about. How much elastic free energy does it cost? Okay, so there is a standard expression for that called the Osane-Frank free energy, which is the elastic free energy of variations. But I have my own sort of personal variation on how to do that calculation. Let me show you my variation, because that leads into what I'm going to say about geometric frustration. Okay, so my variation is based on thinking about what are all the first derivatives. So how can the components of n, x, y, and z components, vary as a function of coordinates x, y, and z, so that it makes a 3x3 matrix, or a rank 2 tensor. Okay, and that can be broken up into three types of mathematical objects. Or, for those of you who like group theory, it's four mathematical objects, or four irreducible representations of the rotation group. Okay, this was a construction first done by these guys, Michon and Alexander, in 2016. What are those four kinds of mathematical objects, right? Well, one is bend. Okay, so bend represents how does the director vary this way. So along the director, how does it tip over, like that, or like that? Okay, so this is a two-component vector in the plane perpendicular to the director itself. Okay. A second type of variation is called twist. Okay. That is a variation which looks like this. It's how the director is turning this way. So pointing this way over here, and then straight, and then back. And it is the same all around, like that. It has to be the same all around because it is a scalar, so it doesn't have a direction. Okay, so this is what Greg Grayson called double twist in his talk a couple days ago, but I just want to call it twist. Okay, so This is a second kind of gradient of n. A third kind is called splay. Okay, so that's when the director is up here and then it goes out this way, and it's the same all around like that. So it's like an ice cream cone, not like a slice of pizza. Okay? And it has to be the same all around, again, because it's a scalar, it doesn't have a direction. Okay, so if you like the word double twist, you can call this thing double splay. Those are three types of director variations that are commonly discussed in the liquid crystal literature. A fourth type of variation looks like this, okay? So this is a mode that goes out this way and in this way, okay? Or if you rotate by 45 degrees, it goes out this way and in this way, okay? So this is another type of variation. It doesn't have a well-established name. I'll just call it the delta mode here, okay? And so this is some fourth kind of way that a director can vary as a function of position. Okay, now we've got these four kinds of first derivatives of the director. The standard elastic free energy is written with this equation on the top. It looks like something times splay squared, something times twist squared, something times bend squared, plus mess. Okay, but the mess can be expressed in terms of these modes that I described, with splay squared, twist squared, and delta squared, so that the free energy turns into this form. It looks like something times splay squared, something times twist squared, something times bend squared, and something times delta squared, which is, of course, what an elastic free energy is supposed to look like, the sum of squares of things. Okay, so this is how I like to think about the standard elastic free energy for pneumatic liquid crystals. Good. Okay, so I've done a cleanup job here, but what do we get out of it, right? Well, one reason why I like this cleanup job is that now it allows us to think about how each of these four modes can couple to other kinds of extra order. Okay, so if you have a liquid crystal, for example, that is made out of banana-shaped molecules, and they have some polar order where the sideways axes of the bananas are aligned, then that creates an environment where the ground state is no longer to have a uniform director, but rather it all fits in nicely if the director has this bend, okay? You could express it as a picture, you could express it mathematically as a dot product between the bend and the polar order, which are both vectors perpendicular to n. Okay, and so this makes a situation where the optimal local state of the liquid crystal has non-zero bend, but zero splay, twist, and delta. Okay, likewise, if you have molecules shaped like cones and there's a population difference between cones pointing up and cones pointing down, then the optimal director configuration has some splay like this, and likewise in the plane out of the board. Okay, and so that makes a situation where the optimal configuration has non-zero splay, zero bend, zero twist, zero delta. Okay. Continuing on with this reasoning, if you have a liquid crystal where there are different populations of right-handed and left-handed enantiomers of the molecules, then that enantiomeric excess couples with the twist, since they're both pseudoscalars. And that makes a situation where the optimal local configuration has non-zero twist, zero bend, splay, and delta. This is what liquid crystal chemists do all the time. Okay. Can someone fix the sound, please? And then there could also be something likewise, a hypothetical situation where the optimal state has non-zero of this delta mode.
Who's their audio on?
Michael, sorry.
Okay, thank you. So then that leads to the question. We've got an ideal director field with a certain bend or splay or twist or delta. But is it possible? Is there any director field with the ideal bend, splay, twist, delta? Not just at one position, but everywhere in space. In general, the answer to that question is no. Okay, and there's a whole history of many years of theoretical research which goes into the answer no, starting with work of the late Robert Meyer, who couldn't fill up 3D space with pure constant bend or splay, right? And then Jim Cessna and collaborators later were working on a model for liquid crystal blue phases, as Greg mentioned briefly. And they tried to fill up space with pure constant twist. It didn't work in flat space, but it did work in S3, in the appropriate non-Euclidean geometry. Okay. More recently, Effie Efrati has shown that in 2 dimensions, you can only have certain allowed combinations of bend and splay which depend on the Gaussian curvature of the 2D surface. Epifanio Virga has worked on something generalizing to 3D flat space and showed that only certain uniform combinations are allowed, twist and delta or bend, twist and delta. And then other people have generalized to 3D non-Euclidean space. We don't have time to talk about it. Okay, so that is a geometric frustration problem, like what we talk about in this workshop. Okay, the director field has an orientational configuration, which is frustrated. There's an ideal local state that cannot fill up space. So what can the liquid crystal do? How does it resolve this geometric frustration? Okay, well, whoops, wrong button. Try again. Okay, well, there's 2 possible answers in general, right? One is that it can fill up space with one of the allowed combinations of director deformation modes. It can have a combination of the mode that it actually wants, that lowers the free energy, and some other mode that it doesn't want, that raises the free energy, but maybe it's worth it to get the thing that it wants. Okay, so we'll just pick one of the combinations from Virga's Italian menu. Okay, alternatively, another possibility is to break up space into domains of the favored mode, approximately pure, separated by domain walls or defects or something like that. Okay, let me show you some examples. All right. So let's begin with the case of chirality, which is the most common case. Okay, so there's some liquid crystal where a chemist has worked hard to make an enantiomeric excess, so more right-handed molecules than left-handed or vice versa. Okay, so it has a favorable twist. Okay, but there is no configuration that has pure twist and nothing else. So one possibility for what the liquid crystal can do, the most common possibility, is to make a cholesteric phase. So that's a phase with a structure like this, where the director field has a variation that goes around in a helix as a function of one coordinate, like that. Okay, and so the mathematical expression for the director field is like this. And if you do explicit calculations, you can see that it has 0 splay, non-zero twist, 0 bend, and non-zero delta, okay? So if you don't think about the delta mode, you might wrongly think that this is pure twist, but it isn't. It's a combination of twist and delta, okay? And so this is for sure one possibility, and so that this happens a lot. Okay. Another possibility, somewhat less common, is for the liquid crystal to form a blue phase. So a blue phase is a more complicated sort of structure where the director field makes tubes with approximately pure double twist. So that's this configuration like that all around. Okay. And it can be approximately pure double twist in some cylinder that's not too wide. And then it can make a lattice with cubic symmetry of these cylinders running in the X and Y and Z directions. And it fills up space that way almost perfectly, except that there have to be some defect lines, topological defects that run in between these double twist cylinders. Okay, and there are different variations with either BCC or simple cubic symmetry. These things really do form in experiments. Okay, so to see the competition between these, right, which is better, right? Well, one either of these possibilities can make the ideal amount of twist. That doesn't distinguish between them. The distinction is what you have to sacrifice in order to get the twist that's desirable. Okay? In the cholesteric phase, the unfavorable thing is that you need this delta mode, which costs free energy. In the blue phase, you don't need the delta mode, but you do need all these disclinations, which cost free energy. So the question is, which is worse of those two things? And depending on energetic parameters for the liquid crystal, either of those things might be worse, which is why both of these things occur in experiments. Okay. Likewise, another example would be if you have banana-shaped molecules, people call them bent core liquid crystals, then you have some favorable bend, but there is no state with pure constant bend. So one possibility is to make this twist bend nematic phase, a phase where the director rotates around a cone like this, okay? That has a combination of bend, which is favorable, and twist and delta, which are both unfavorable, but maybe that works out to be the best on balance. Or you could make something else like a splay bend nematic phase, where you can have regions of almost pure bend separated by domain walls, and then you can get the bend on the next domain. Okay, so I have similar stories for modulations driven by splay or the delta mode. I don't have time to talk about those. So let me just summarize with this table, okay, that you have these four modes. Each of them could couple to some kind of molecular order, but then it's a frustrated state. You have to think of what compromises you can make to get the best possible director field, which might have uniform deformation modes or it might have defects. Okay, and so basically, my speculation is that's why liquid crystals have so many phases, right? That there's only four things that might be favorable, but they can't be achieved without frustration. And so frustration is what leads to the richness of liquid crystal phases that so many of us know and love. All right, with that, I'll wrap up and thank you very much.
So
Effie.
borrowing on you said how this is like exactly like packing. and I think of packing of spheres. So the analog in my head now says we saw yesterday that spheres would like to make tetrahedra. Tetrahedra do not isolate space. Is that what we have so many crystals? I mean, how, did you obviously thought about this analogy?
Yeah, well, I mean, if we think about some of the problems, say, that Greg showed us in our first talk, right? There are situations where you have a frustrated packing problem. And so then the question is how to resolve that frustration, right? And commonly in that situation, it happens with this self-limiting growth, right? And so that you would have the approximate ideal packing in a limited region, and then you have this packing in another limited region over there, right? And in between, they have to be separated by something, okay? And the something might be empty space, or it might be some kind of defect, right? As the crystals get packed together, some sort of grain boundary, okay? So that I think of as an analogy with my second type of resolution. Okay, the first type of resolution corresponds to something else, right? Where you make a local distortion that changes the packing problem to something that can fill up space. I think this was Randy's comment after one of the talks yesterday, right? That instead of trying to pack dodecahedra, which don't fill up space, you could distort the dodecahedra into some other related shape that will fill up space perfectly, okay? And so that would be something analogous to my first thing, right? Where locally you change what you want to pack, right? So that it is not as favorable locally as the thing you started with, the perfect dodecahedra, but it's good enough. And then you can pack those things everywhere. So those are the kinds of analogies I was trying to think through. Please.
Yeah, you mentioned these like deformations in bend, and mentioned that they can couple with like twist or a splay to form these like twist bend and splay bend phases. But I know that like you can also couple like the bend and the twist to make these like double twist type cylinders in these like bent core liquid crystal structures. But I think people normally talk about them as if they're being like metastable. Is that because there have to be defects in there, so they're always going to be unstable compared to the the helical structures? Or can you see a way to stabilize these?
No, these things that I'm presenting are stable, I would say, not metastable. I'm not talking about kinetics here at all, right? And so, in the double twist cylinders, like in this picture, right? The cylinders are approximately pure double twist, okay? That is right on the central axis of each cylinder. It's exactly double twist, right? As you go farther out, you blend in some of the other deformation modes. I guess not split, but you blend in some bend and some of the delta mode, okay? And so that's where they become less favorable, okay? But what's driving this is the negative favorable energy associated with the double twist, okay? And then the fact that it can't extend to fill up space, that creates the self-limiting growth, you could say, of a cylinder. And that's why it's better to stop the cylinder and make some other cylinder over there. Okay. So that's the best possible compromise. is no state that's better than this, right? That the bend is an unfavorable thing for this material, okay? Now, for a different material, this represents a different kind of molecule synthesized by a different chemist, okay? And this material has a negative free energy associated with bend. And then there's a separate question of, well, how can it achieve that negative free energy? But again, I'm only talking about the stable states. The metastable kinetic states are a further issue.
Yeah, well, I guess I was asking, is there a way to stabilize like a double twist cylinder with these types of bent molecules?
Oh, I don't know. I don't think so. Okay, so that's an interesting point, right? That because there is bend in here, could you make this kind of thing that's favored by that amount of bend? I don't think so, because there's not so much bend, right? And you would have even more bend if you extended it farther out, right? But if you like bend, you might make something like this, which would be extended uniformly out of the screen. So that would also make more or less cylinders, right? The honeycomb is sort of cylinders coming out of the screen. So that would be the cylinder-like structure stabilized by bend.
Thank you.
Greg?
Maybe we could go back to your slide about which is worse one. This is one of those comment questions. I mean, I think the way you said is really nice, that you can get these domains that are approximately correct, right? And then you can try to glue them together, defects.
Mhm.
And I guess I would advocate for like thinking about, those are really two different types of problems, right? Which have two different types of energetics, right? There's sort of the cost of approximately not getting what you want,
Mhm.
right? Which may or may not involve defects that are sitting between the things you're gluing together. That would be the case where you've just decided, to break away, form your own group.
Mhm.
And then the case where you have to fill up space, or you have a strong incentive to fill up space with whatever, some experimentalists putting a lot of stuff in there.
Mhm.
And so I guess the kind of general, I mean, this long time ago, this idea you could melt the blue phase right into a bunch of tubes, where in between you have isotropic stuff. I mean, is there a general understanding of like how, in your mind, of like when is it better? I mean, defects don't interact just like a surface energy. Sometimes with line energy, sometimes they have long range interactions. Kind of how to think about when it would be better.
Yeah. So is that an experimental fact that you can melt a blue phase into separate tubes, or is that a speculation?
That's a speculation. I mean, there's certainly problems where instead of, maybe it's because it's trying to form something more complicated like a columnar structure, things will double twist and not try to glue together. And maybe the frustration is different than what you're saying, but as a general sense, like in terms of the problem, you could frame it in that way.
Yeah, so there are definitely, other liquid crystal systems where you get disconnected structures, right? So helical nanofilaments, for example, right? Where instead of having, some bathtub full of liquid crystal, right? That's all sort of connected together. You get a whole bunch of separate structures, and in between would be the melted isotropic phase of the same material, right? Or if it's a two-component mixture, maybe there's just the water, aqueous solvent in between, right? And so that is definitely a possibility, right? Is to give up on connecting these structures with any sort of topological defects or domain walls, and just have disordered stuff or vacuum in between.
Right. But there's still frustration, right? I mean, it's just.
But then there's the sort of self-limited size of the individual structures. Do we have time for one more? Yes? Sure. Please.
This is a naive question, but I'm curious about this cholesteric phase that you're discussing here on the left.
Mhm.
I didn't I'd never heard before that that even if you have a preferred twist, this is not fully happy. It also has this delta thing, which I don't really have any intuition for.
Yeah,
So,
so this,
Um,
oh, I'm sorry, please go on.
I'm wondering basically these days, how much control do clever chemists have over these different energy constants? For example, the one in front of the delta, like can a clever chemist these days design an organic molecule that doesn't care about delta, for example, so that this state can be completely happy? Or is that kind of designer control of these kinds of constants still very hard?
That is not really available. Okay. And so in the free energy, right, there are 4 modes, so there are 4 coefficients. Okay. 3 of them are very well studied. Okay. The remaining one is very difficult to study, the thing called K24, right, which is the coefficient of delta squared. Okay. And so there are some experimental measurements of that. You have to do tricky experiments where you work in a finite tube or compare different tubes, that sort of thing. And so it is not very well known. And known is even different from controllable, right? And I have not heard of chemists trying to control it intentionally, right? And if anyone were trying to control it intentionally, the motivation for that would be trying to make blue phases, right? Whereas trying to make a cholesteric, I mean, nobody's going to do extra work to try to make a cholesteric because there's lots of cholesterics out there anyway. And so if anyone were trying to make blue phases, they would try to make the K24 bigger, not smaller.
Okay, well, thank John. Thank you.
Thank you.
Eight carbon.